I'm good. How are you?
Good. These last classes, I realized I always finish right on time. Like I'm always.
You're fantastic.
But not. I should finish 5 minutes
Don't
earlier
worry
in
about it.
principle, right? But yeah. I
Honestly,
was
don't worry about it.
rapping.
It's okay. That's the nice thing about finishing at 6 o'clock because there is no class afterwards. So I can
That's true.
continue.
So in case, yeah, I don't know if it's good. Yeah.
Or I have
or
like
exactly.
an incentive.
You don't have
to-
an incentive to finish,
Exactly.
right? I'm like, Steph is here. He wants to come.
Exactly.
Enjoy the class.
Thank
Yeah.
you.
Thanks.
See you soon.
Yeah, see
Thank you.
soon.
Yes, you're coming on time.
All right, let's make a start. Welcome, everyone. I like the topics of today. We're going to talk about air pollution. There is no problem set. Just a reminder, there is no problem set for these seminars. There is only one paper that you need to read. It's quite long, but sorry about that. Only one paper, okay? So at the last slide of this lecture, you have the paper, but it should also be on your reading list, etc. So today we're going to talk about a topic, which is obviously air pollution. We're going to talk about the economics of air pollution. And let me start this lecture by giving you a bit of motivation, try to persuade you, if you're not already persuaded, why I think that air pollution is something that is important for all of us. Environmental economy is not, because it really affects a lot of stuff. So let me start with some motivation slides. So ambient air pollution has been high on the agenda for years and years and years. Kind of going up and down in the news cycle, depends on what other things are. But you know, according to the WHO, air pollution has worsened in many, many cities and places around the world, and also importantly in places that were already quite polluted. So we see a deterioration in places that are polluted that are getting even more polluted. It's not always the case. Some places are getting less polluted, and we're going to talk about it today and what kind of lead to kind of these differential trends that we see across the globe. All right, so we're going to look at that. I always kind of like, you know, use this quote to motivate, and this is what Maria Niera, the head of public health at the WHO, said. She keeps saying that in kind of different variation. This is in an article for The Guardian, from an article in The Guardian. She said, "We have a public health emergency in many countries. From pollution is dramatic, one of the biggest problems we are facing globally, with horrible costs to society." So today we're going to try to think about what are these costs. What are we talking about here? Okay, and is it really the case? How bad the situation is? Let's think about, you know, something beyond just the big headlines that we see sometimes in the news to kind of try to understand what's the real issue here. Talking about headlines, that's another headline from the same year, 2016. Look at that. Air pollution causes 467,000 premature deaths a year in Europe. Almost 500,000 people, according to this headline, almost 500,000 die prematurely every year in Europe from air pollution. That's a big number. That's a really, really big number. So one, is that right? We're going to talk about that. But second, if it is right, we all need to worry about that. Think about all the things that we worry about right now, you know, or we were worrying about, or you were worrying about throughout your life. Almost 500,000 people die prematurely in Europe. We're not talking about places, you know, that you think are very polluted, and they are, like, you know, places like, for example, India, that has a massive problem with pollution. We're talking about here in Europe, right? So we're going to explore that today as well, okay? Right. If you need some more motivation to kind of tell you about how problematic pollution is, so this is a figure that I took from the Air Quality Life Index, published every year. This from from the 2023 edition, published by the University of Chicago. And this just show you a selective, you know, a select kind of reasons of why people dies. You know, we tend to think that alcohol abuse, for example, it's a significant cause for premature death, or drinking unsafe water, definitely smoking. But it looks like pollution is, you know, really at the top here. Same kind of effect or same kind of impact on mortality as smoking, essentially, and tobacco. Okay. So again, we're talking about, this is from 2023. This is not something that happened in the 1950s, right? You know, there is a really good reason to do something about that. If this is true. Okay? Because this is one of the leading cause of life being lost. Okay, this is just in terms of how many years on average being lost because of the kind of different type of issues. And as you can see here, pollution is at least among these kind of things is the highest one. Okay, obviously how it's going to look across geography, how it's going to look across the world is going to be very different. Okay, you might going to find part of the world that contribute more to this effect than other parts. Okay. And that's due to a variety of different things. One of them is obviously the level of pollution in these places, okay? So where you have more pollution compared to, in some places you have more pollution compared to others, but it's not the whole story here because you can imagine two places that have exactly the same level of pollution, but you're gonna see different level of mortality, and that's gonna be because of different things. For example, the healthcare system that you have in your country and how that can potentially help you to prevent deaths that are induced by pollution. And there are some other things. This is just one example, right? But this is that also might explain the kind of the differences across country, not just the level of pollution. So there are two things here, okay? The level of pollution that varies across space, but also other things that matters here in terms of this relationship that also very, very important. All right. So this is what we got. So I hope that by now you're kind of interested. I hope. I mean, it's kind of a compulsory course for most of you, so you're going to have to sit here anyway. But I think that should kind of, every sensible person should look at that and say, okay, I'm interested. Let's see what Sophie has to say about that. All right, so outline of today, I'm going to start with a bit of background, tell you where the literature kind of began and how it kind of evolved over the years, starting from papers in the 1930s and quickly kind of coming towards where we are right now, talking about identification issues. So what are the problems to kind of try to estimate some of the figures that I mentioned here? Are these figures based on any causal evidence, or they are just kind of, or not, just correlational studies? And lots of back of the envelope calculation. We're going to talk about that as well. So we're going to try to think beyond that and kind of try to think about using the toolbox that you acquired here in your prior education about causal inference. So we're going to talk about that, a potential solution to deal with identification strategies. For those of you that are taking GY426, it's going to be very related to what you were doing in the last 2 weeks. Specifically, you did IV, right, on Friday. So Steven and I kind of coordinated, and we're going to talk more about IV, so I'm going to help you also with 428 today a bit. For the econ students and the PhD students, you should already know it anyway. So we're going to talk about solution in terms of kind of from the theoretical perspective of that. And then we're going to spend a lot of time on looking at solution in action. So we're going to go through some empirical papers and see how we implement the different solutions that we suggested to overcome these identification issues. We're going to talk about cost. You know that I like cost a lot. So we're going to spend a lot of time on that, kind of link everything that I'm doing here to what we did in kind of week 2 to 6. Okay, how is that related to the, to the diagram that I showed you? We're going to try to think about that. And then we're going to talk about what we can do about pollution. Pollution is a big deal. We're thinking about, the marginal damages. We're thinking about the cost and all this kind of different stuff. Is there anything that we can do about it, and how we as an economist help to do something about it? I'm not going to talk about everything that we can do. I'm going to show you something around that. Happy to talk more about it during the seminar. We will talk about more. We will talk about it more in the seminar, in fact. And then, if we have time, I will share with you some of my thoughts about, how I think the future is going to look like in this sphere in terms of research, at least. Maybe even policy. But we can talk more about that again in the seminar. Any questions before I start? No. As always, feel free to ask questions, give me comments, tell a joke, whatever you want. All right? All right. So where this literature actually began, I mean, pollution is not a new thing at all. You can go back to the Romans' time, and people were complaining about pollution. but kind of the recent literature started, I think, fair to say, around the 1930s, not in economics, surprise, surprise, in epidemiology. So early studies in this field examined the effect of severe air pollution episodes on mortality, okay? When I say severe, I mean really, really big cases when we have very, very high level of pollution, all right? And the way that they did that, they just report on strong link between mortality and radically elevated concentration of particulate pollution and sulfur oxide by simply comparing counts of death before, during, and after extreme pollution episode. And again, I keep saying extreme because this is not the type or the level of pollution that we tend to experience here in London at this day and age. Okay, so one really kind of famous episode is the London Great Smoke that happened in 1952. You probably recognize this beautiful picture here. This is Piccadilly Circus. I'm sure that you all visited this place. If you haven't, you should. It's a really nice area. Kind of just next to Regent Street. Actually on Regent Street in a way. And basically, in 1952, let me give you some more detail what happened. There is a smoke, a fog that covered the capital from basically for a weekend, from Friday, 5th of December. So actually, it's like 4 days from today, right? To Tuesday, the 9th of December. About 4,000 to 10,000 people were known to have died as a result of the fog, but it could have many more. This is just in one weekend in London. Just to kind of, that you will understand what we're talking about. 4,000 to 10,000 people died. Okay, potentially even more. It was so severe that in many parts of London it was impossible at night for pedestrians to find a way, even in familiar districts. People just couldn't walk around. Press reports claim cattle at Smithfield has been basically choked to death, and travel was disrupted for days. So planes, London Underground, and obviously traffic, cars. And the reason why I'm saying that, all of this stuff, I mean, obviously people died, but there is a variety of costs that are associated with this episode of pollution. It's not just the death count, which is obviously massive, and we're going to have to think about how we actually, monetize that. We're going to talk about it today. But also other things happen, and also we haven't even talked about morbidity. People that end up in hospital not dying. This is also very costly to the NHS and also for the people themselves, obviously, because no one want to be ill, and then they can be off work, etc., etc., etc. And then I kind of really wanted to show you that, but the sound doesn't work. I can try it once more. This is from The Crown, episode from The Crown, that it's exactly about the Great Smoke of 1952. So I try to, let's see if it works now, but I tried to make it work before, it didn't. But let's see if it works now. Okay, it doesn't work, but maybe you can just see in the background. Nothing works for me, I guess. Anyway, you can watch it at home. I'm going to go back to the slides. The point that I'm trying to make is that it was, sorry. Please watch it at home. It's on the slide. So it was really, really big and really affected everyone. Okay, and there is some nice kind of episode around that in The Crown, if you're interested. What led to the smoke? So it's kind of a combination of two things. So first of all, London, at least back then, has a pollution problem, right? So lots of pollution was generated in London from factories, from cars, etc., etc., etc. But that's not the all of the story. What happened at the same time is that we have they had the temperature inversion. Okay, that's going to be useful for you later on in this lecture. Basically, it's a weather condition. So let me explain what it is. So basically, when you go on an airplane, right, and you have a screen in front of you. I don't know, I have a screen in front of me, and I always like to look at the map, right? And when you go up, you see how temperature dropped. You know that? But basically what happens when you have a temperature inversion, you get a reverse. So that you go up and temperature is a bit higher. And that's what happened when you have that. This is something that naturally occurs, especially around the winter months in the United Kingdom. When that happens, what it does, it traps the pollution near ground level. So you have the ongoing emission that happened in London that normally is just going to disappear, but now you have this warm kind of layer on top that prevents the pollution from going up. And then pollution, the emissions start to accumulate over time, and you get this type of episode. Okay? Remember this, called atmospheric inversion. Remember that. That was a big, these two things together, that's what led essentially to the London Great Smoke. Remember that, okay? Because we potentially can use that later on. Okay? So that's what's going on. The other reason why I keep going about the London Great Smoke, because it was so big and so severe that led to change in legislation here in the UK around air pollution. So one is led to the Clean Air Act of 1956, which did lots of things. For example, change where the location of industry, introduced the concept of smoke control areas, SCAs, right? So for example, if you are in London right now, I don't want to go into more details, but there's some restriction about, for example, how you can use your fireplace, if at all. Okay? And all these kind of different things came from this experience, and therefore, and which led to legislation that people kind of realized, look, we can't have that anymore. Okay? We need to do something about it, and they did, right? So this is kind of, I guess, the direct effect on legislation. Again, main thing is kind of reallocation of industry, smoke control areas, and I guess some financial subsidies that were provided to change the heating system in London as well. Also, the Clean Air Act of 1968 also related to this experience. It was really kind of, a significant moment in relatively recent UK environmental legislation. All right. So this is about the London Great Smoke. Again, something that can also be used in a way in a study, if you're kind of interested in historical studies about air pollution, because there is kind of change in legislation. You can think about, for example, how the staggered introduction of the SCA, the smoke control areas, had an impact on pollution or other stuff as well, right? And I'm happy to talk to anyone that's interested in this line, because we were working on that with some co-authors recently. Okay, so this is kind of the beginning of the literature. Again, talking about very severe cases of air pollution. I keep saying severe, because again, nowadays in Europe, we don't see such levels anymore. Because of legislation, which is good news. So the later research evaluated the relationship between lower and what I would say more common level of air pollution in the United States and in UK and Europe, and also found that even at much lower levels, things that we kind of experiencing nowadays, there is a strong link between pollution concentration and mortality. One of the most famous studies in this literature is what we call the Harvard 6 City Studies. It was published in the New England Journal of Medicine, one of the most prestigious journals in the world. And basically, they did more than just kind of compare counts before, during, and after. This is kind of what they did before, as I mentioned before. So really, more than just this cross-sectional variation. They managed to, in here, for example, it's a 1993 paper, they managed to adjust for individual risk factors. So they have some more data and did something that is slightly more, more robust. And what they found that there is a strong and highly statistically significant association between reduced survival and community average fine particle or PM2.5 concentration. After adjusting for individual risk factor, life expectancy was estimated to be reduced by approximately 2 years in the dirtiest city compared to the cleanest, okay? Two things to say about it. First of all, when we say dirtiest and cleanest, at the time, none of these kind of areas were in breach of the EPA regulation standards. Okay, so it wasn't the really the dirtiest parts of the United States compared to the cleanest. All of these kind of areas that they looked at were within the standard. So this is the first thing that I want to say about that. And then in terms of the magnitude, this kind of 2-year effect, right? What are we talking about? This is at a time, right, was compared to eradicate all mortality that comes from cancer. So another way to put it, if back at the time you would basically find a cure for cancer, you would save this amount of years on average, 2 years. Right at the time. So that's a huge impact on life expectancy. That's what I'm trying to say here. It's the equivalent of finding cure for cancer. Okay? According to this study. And again, I'm not talking about the dirtiest part in the United States compared to the cleanest one. I'm talking about both kind of the treatment and control group, if you want to think about it in this way, were within the standards at the time. It's important that this study also important because that's kind of, I think, among other studies, but this study really kind of drove this home, is that this is why the EPA started to regulate PM 2.5. What is PM 2.5? What is particulate matter 2.5? So in general, it's kind of a catch-all pollutant, so it just depends on the size of the particle. So we can think about different types of PM, particulate matter. You can think about, normally now we think about two sizes, PM10 and PM2.5, so it just depends on the size of the particle. So if it's less than 10 microns in diameter, this is PM10. If it's less than 2.5 microns in diameter, this is 2.5. Just to kind of explain to you the sizes here, it's so small, PM2.5, and that's an important bit. I will explain why. So just to kind of give you an understanding how small it is, what you see here, this gray thing here, this is straight from the EPA website. This gray thing in here, this is human hair, something that I used to have, right? So it's very, very small, right? And inside this hair thing, right, you can see here these blue dots, this is PM10. This is the bigger particle. And within this blue dot in here, you see this purple dot or pink, whatever that is. This is PM2.5. So it's tiny. It's something that you can't really see in the naked eye, but that has implication to a variety of different things. Some of it I will talk to you about. Some of the things that around that I will talk more on Wednesday. But one is something that you can't really see. Two, the smaller the particle, the greater the health impact that it causes. Why? Because it just managed to penetrate deeper into your body. So it basically crosses certain barriers and it can reach your bloodstream, the brain, etc., etc., etc. By the way, TSP, which we discussed, I think, last week when we talked about the paper by Michael Greenstone about the Clean Air Act, this is essentially PM100. All right. So over time, the regulation moved from like PM100, PM10, PM2.5. Now there is discussion around PM1. Yes. This is a great question. I spent a lot of time thinking about it and talking to many, many people about that. Because you're right. It just depends on the particle, but you don't know whether the different composition of PM2.5 have different impact on health. So I'll talk to many people that work on health, not economists. You'll be shocked. Including the Frank Kelly, that is kind of the guru of air pollution here in the UK. He's a professor at Imperial College. We're doing some things together. And he's a toxicologist, so he really kind of understands that. And what he told me, and this is kind of where the science is, he said, like, look, the truth is that we don't know. So our ongoing assumption is that it is. It's kind of the same. This is also what the WHO assume, and pretty much every legislator, to the best of my knowledge. They are, I think the people at Imperial, they are the first people in the world that actually publish data in London, actually, about the composition of PM2.5 to the public. So you can actually go onto the Imperial college website and get this information. But even if they have this information, because basically I want Frank to kind of help us with the paper that I'm going to show you on Wednesday to understand your point. And he was like, look, Sefi, even if I knew the competition, I wouldn't be able to tell you much about that. We're not there. So there is lots of work on that. I know that they are measuring in some homes in West London, something around that, but lots of work to do on that. It's extremely complex. Again, that's a great question. Ongoing assumption, all the same. It's probably not, but this is where we are right now in terms of science. Great question. All right. So this is PM 2.5. All right. So again, the smaller the size of the particle, the greater the impact on health and other things as well. Also, we're going to talk more about indoor pollution on Wednesday, but it can also penetrate into houses better, okay, compared to PM 10, for example. So the size of the particle also will have an impact on the outdoor-indoor relationship, which, as I will try to convince you on Wednesday, is quite important. In general, the epidemiology literature also discovers a strong relationship between ambient air pollution and morbidity, not just mortality. We're talking about deaths, but death is an extreme case, right? But you can be affected by air pollution in other ways. So this is some of the things that, I think this is from the EPA, so I didn't put a source here. So things like cancer, heart attack, asthma, chronic bronchitis, decreased lung function. There is much more that we know from economics with causal evidence. Things like dementia is linked to pollution as well. You name it, it's linked to pollution, pretty much, in terms of health outcomes. These are all like kind of big, scary health outcomes, but also smaller things like irritation of the eyes, nose, and throats, headache, dizziness, and fatigue. Seems like potentially almost irrelevant. Who cares if you have a headache? But we do care because we are economists, and that might affect your productivity and your performance at work. So, and then when you aggregate that across the workforce, that can have a huge impact, actually. And I'm going to show that on Wednesday as well. In fact, that's probably going to be the biggest one in terms of the cost. Okay? And I'm going to show you why. It's just because it looks like nothing, but you're like, oh, I'm not feeling 100%. I kind of have a headache. I'm a bit tired, whatever. Are you going to work as well as you would work if you feel like 100%? Probably not, right? Think about you studying for an exam. We're actually going to talk about that today. So these small things seems like, who cares? We care. Okay, that's my point. And I'm going to quantify that on Wednesday for you guys, all right? All right, any questions so far? This is kind of the background, everything you need to know how the kind of literature evolve over time. But most of this literature is kind of correlational. And you know that correlation is not causation. So, the point is that you can't just run these simple OLS regressions and expect to get causal evidence, because in order for the OLS to provide causal evidence, we need a bunch of assumptions around that. So this is kind of the assumption that you normally study in your econometrics class. This guy here, the covariance of X and the error term should be equal to 0. That's the guy that's going to cause us all the problems. Okay? Most of them, at least, all right? So basically, if we assume that all these kind of assumption actually hold, we can say that, this is kind of the Gauss-Markov assumption, right? OLS will give us an unbiased estimator, right? So we're going to get what we call BLUE, best linear unbiased estimator. So it's going to be unbiased. It's also going to be the most efficient estimator. The problem with that is this guy here, is assumption 4. That's what's going to cause us significant amount of headache. Not just the pollution going to cause us the headache, also that, right? So we're going to try to think about what can we do about that. So what do you think? What can we do in order to overcome this covariance of X and the error term not equal to 0? What can we do? Yeah. Robust standard errors. So what is that? So the X and U not equal to 0, Let's kind of deal with omitted verbal. Let's kind of talk about omitted verbal bias mainly, right? So we're going to have the issue with the standard errors. I agree with that. But how are we going to deal with the OVB? Yes. Yes. So this is one kind of way to deal with that. We can run an RCT. Sorry, you have a question there?
Yeah, I have a question regarding the assumption 4.
Yeah.
The covariance assumption. Isn't it like the assumption we need for consistency?
Well, we need it for unbiasedness as well.
Yeah, but for unbiasedness, I think we also need the mean.
No, we need many assumptions. We need a variety of different assumptions. But what I'm saying that for unbiasedness, we need a whole bunch of assumptions, specifically this one. And if this doesn't hold, you have a bias estimator.
Yeah, but do we not like additionally need the mean independent?
No, we need
Instead of
more assumptions. This is not the whole all of the assumptions that we have here. Okay. The point here is that if any of the assumptions do not hold, we're going to have a bias estimator. I think you're talking about IV and we're talking about CLIM, and I will go towards there in a few slides. If you're thinking about the consistent estimator, but if you're going to get a validation of this assumption, your estimator will be biased. Okay. Now you were right. One way to deal with that is basically, as I said, the gold standard of causal identification is running an RCT, a randomized control trial. The problem with that, potentially, I don't know if you will agree with me, for the thing that we care about, I don't know if we can run an RCT. Can I say, look, you guys going to be in the treatment group, you guys, lucky, you're going to be in the control group, I'm going to put all of you in a room, start to inject lots of pollution, see when you die. Compare it to the outcome of this guy. So I'm never going to do that because I like most of you. No, I'm joking. I like all of you, right? I also like you. Look, don't get, this is why I put you in the control group. Don't tell them. But we can't do that for various reasons. One is unethical. Second, like, who wants to do that, right? So with this literature, we are a bit limited with using an RCT. That's my point. We can use it sometimes. In fact, this is what I'm going to show you on Wednesday. We did exactly that with some element of this issue. But if you care about, for example, health, and pollution, mortality and pollution, you can't really do that. So what we're going to do instead, what else can we do? So we can't run an RCT. What else can we do? Natural experiment, right? Anyone can give you some examples? Roughly, yeah. For methods that we can use, yeah.
Methods or like for policy experiments? I was thinking about.
You name it.
I was thinking like enacting a policy, a cleaner act policy.
Yeah.
Force sources of pollution to vary naturally, and then you can use that as an exogenous source of variation.
Absolutely. Policy change. That's what we used last week when we talked about hedonic, right? The paper by Michael Greenstone, right? The Clean Air Act. Remember? Some places we did kind of this diffs and diffs study. We talked about it during the lecture. Some places were affected by the change in policy, some are not, and we look at the differences before and after that. So it's a combination of diffs and diffs and change in policy that enable us to do this kind of, use this kind of what we call a quasi-experiment, so an almost experiment, because we can't necessarily run an experiment, but something that is related to that. For example, we talked about the house prices study that they did, but I think they have another study that do exactly the same thing with health as well, right? So we can look at that. So this is one of the things. We don't have to use a policy change. We can use something else, for example, and we're going to discuss some other things that we can use. Hint, I already gave you one possibility, something that we can use when we talk about the London-grade smoke. Something that happened almost at random, or maybe in a combination with things, we can argue that that's as good as random. That's something that happens naturally. Okay, we can use that in order to create this setting that you want to create, this RCT, but we can't do that, right? So that's basically what we're going to do. Use things like change in policy, use some climatic conditions or change in climatic conditions, all these kind of things that create this random variation in pollution, and then we can link that with some health outcomes or some other thing that we care about. All right. So this is where we are. The issue that we have, one second, more broadly, it's not just about omitted verbal bias. We also need to worry about measurement error. For example, do we have perfect measurement measure of pollution concentration, or more importantly, pollution exposure, because what really matters here for health is not about the concentration. It's about how much pollution you're actually exposed to. And potentially there is a massive variation in pollution even within small geographical units. Okay? And what really matters is pollution exposure, not pollution concentration for health. Again, our paper on Wednesday going to talk a lot about that. But you can imagine if you are sitting here, the pollution here, is it the same as the pollution that you will experience if you're going to be on Kingsway? Probably not. Is it higher or lower? I don't know. I don't know. That's the point. Yes, sorry, question.
But like even with policy changes, isn't there still some form of like homogeneity? Because you probably assign a policy to a region that's already more polluted than a region that's not.
Totally. So this is totally agree with you. So some of the time, yes, some of the time not. So for example, think about the paper that we discussed on Wednesday last week when we had this kind of discontinuity on the superfunds. So here, yeah, I agree with you. Obviously, we want to clean the most hazardous, but there is some kind of error, and around this community is as good as random. Nothing going to be perfect. This is why it's called quasi-experiment. It's not a perfect experiment. With the point that you made about changing the Clean Air Act, yes, it's also not perfect, but it's the identification assumption that you need in order to claim causal inference are significantly reduced compared to other methods. Specifically, if you combine that with things like this and this, things like that. But I agree with you. It's nothing that I'm going to show you is going to be perfect. It's going to be almost perfect. Quasi-perfect, yes.
On the exposure question,
Yeah.
do we know what those response functions for PM2.5 are? Or?
No, we don't know exposure. I'm going to tell you more about it on Wednesday, okay? We are working on that quite a lot, including what I'm going to tell you on Wednesday, but also on Wednesday I'm going to tell you about an ongoing project that we got funding. We are starting the experiment in the beginning of next year here in London to really get at exposure. So this is a new study with Arik Levinson from Georgetown University, Professor Georgetown, and Lutz Sager, which is a former student. Here, he used to be at Georgetown, moved back to Paris. So we kind of worked on basically get the full exposure of individual and try to do something about behavioral change in London. But we can talk about it more on Wednesday. Where was I? Right, so we have that, we have measurement error. We also have reverse causality issues that we might need to think about, okay? So, it could be that, for example, if you think about, well, we're gonna come back to that later, actually, when we talk about some papers. But it can go the other way. You can think that pollution caused something, but it could also be that the other thing caused pollution. Okay? So I'm gonna give you an example later on today. So what can we do? You said correctly, we can run an experiment, not necessarily gonna work. In some settings, we can do something else, quasi-experiment, not perfect, agree. We can use change in policy. We can use something else that happened in terms of the weather that will create this kind of experimental design. We're going to use all of it, to be honest. That's our best strategy here. All right. Let me kind of remind you two things before we potentially going to take a break, and then we're going to talk through a bunch of papers. So one thing that we're going to use quite a bit is instrumental variable, all right? I'm not Steven. Steven is much better than I in econometrics and in everything. I'm not going to give you the whole kind of everything that you want to know, all the assumption that you need for IV and everything like that. So before we kind of, this is not the course, but I'm going to just remind you what we need from like high level, all right? So we need, here we're going to talk about consistency. We're going to talk about IV, right? So we're going to talk about law of large numbers. We're going to think about large sample size, which is important because I saw some IV studies with very, very, few observations, and then you kind of try to think about, can you run an IV with like 40 observations? If we think that how you prove IV, it's about consistency, it's about when it collapses to the mean. But anyway, what's the intuition behind IV? So we have this kind of equation here. We have Y on the left-hand side. You can think about it as some health outcome that you're interested in. Then we have beta x. Beta is the coefficient of interest, so you can think about x as pollution. And then we have an error term. The issue that we have here is that x is correlated with the error term, okay? And this kind of machinery that we're going to use here, going to work with omitted variable bias. We're going to help us with measurement error and also with reverse causality. So IV going to buy, basically what IV going to buy you is quite a lot. It will deal with all of the issue that most of the issue that we are worried about. All right. So what's the intuition here? Okay. Again, big picture here. There is a variation in x, okay, in the endogenous variable that can be divided into 2 bits, okay? The bit that is correlated with the error term, this is what causes all the problem. And then there is a bit that is uncorrelated with the error term. What's the instrument going to do for us? It's going to take only the bit that is uncorrelated with the error term, and it's going to isolate this variation, okay? So the instrument basically picks out the variation in the treatment that is uncorrelated with the error term, allowing us to estimate a causal effect. Again, this x here, 2 bits of variation, some of it related to the error term, that's the source of the problem. Some of it is not. We're going to take, the instrument will take the variation that is uncorrelated, and we're going to use that, and then we're going to get a consistent estimate, okay? A causal estimate as well. Broadly speaking, we can think about 2 conditions that our IV need to satisfy. You can think about it, the second one, you can think about 2 different conditions, but the first condition is that x and z, the covariance between x and z is not 0. This is essentially the first stage of your regression, right? So you can see whether there is a correlation, high correlation between the IV and the endogenous variable, okay? Again, this is the size of the first stage. Essentially what you're going to look at is at the f-stats of the first stage. There is a lot of literature, a lot of discussion around you need f-stats above 10, above 20, above 30. I kind of lost interest in what's the right number. You just need a good instrument, to be fair. That's how I think about it, that it's not like, flaky. So that's kind of the first thing. The good thing about it is you can actually show and prove that, you have something. There is a statistical test for that. The second one is that the covariance of the instrument Z and the error term is equal to 0. This guy in here can be, this condition here can be broken down into 2 different conditions, to be fair. You probably heard about it, the exclusion restriction and, the independent stuff. That's okay. We're just going to think about it in terms of that, Z and the error term. What's that? That's basically, if we don't have that, we back in to square one, right? Because that's the issue that we had with X. So this is what we're trying to solve here, essentially. And there is no way to prove that, right? We're just going to have to tell a story and kind of hope that people will buy it. And that we will buy it as well, I think, which is more importantly, at least to me. But I know that for other people, the other one is more. So basically, you need to make a convincing case why your instrument satisfies these conditions. There is no, to the best of my knowledge, correct me if I'm wrong, there is no single test that can actually verify that, you got it right on this one. Okay? So again, this is the 2 conditions. You can break down this one into 2 different ones, the independent assumption and the exclusion restriction. We're not going to talk about that today, but that's kind of the main point, right? So this is one thing that we're going to use quite a bit because it buys us a lot. The other kind of method that we're going to use, and again, I'm just reminding you things that you covered before, is fixed effect, okay? Fixed effect can help us a lot. It's much easier. Basically, we can use it quite a lot, especially if we have panel data. So we, for example, observe the same individual over time, all right? So we have a time dimension in our data set. And that can help us to deal with things, omitted variable bias, or omitted variables that are not time varying. Let's put it like that. All right, so for example here, and I'm not going to go through this whole proof. Let's say that we want to explain some outcome and we care about some different, let's say, independent variable, right, different axes. It can be, you probably study that in terms of education or in terms of pollution or something else, doesn't matter. And what the problem that we have here is that we have this alpha I here, which is kind of, let's say, if it's in terms of education, it's kind of unobserved either because we don't have access to the data or because it's very hard to actually observe that, like something like talent or I don't know, right? If you have this information, right, notice that here on the left-hand side we have IT, so the variation here changed between individual over time. Here we just assume that that's kind of constant over time. So for example, the talent doesn't change. You have the same talent, it's kind of inherent. So if you use this fixed effect, basically this is y bar, so this is kind of the average that you take everything, because this is time invariant, right? So the average of that is going to be exactly the same. You can basically subtract this guy from this guy in here, and alpha I going to go away. Essentially, you basically kind of partial out all the time invariant unobserved factors that you have. The problem that you have here is that if there is no other things that kind of helping you, you're not going to deal with one, time varying factors that are unobserved, two, measurement error, three, reverse causality. So this is kind of the thing that I use the most. This is why I kind of brought them in. But you need to know what each of these methods actually buys you in terms of identification. Now, let's take, until, I don't know, like 10-minute break, and then we come back and talk about papers, okay? We're not talk about theory anymore. Sorry, anyone had a question that I didn't answer? Okay. Let's come back at 5, all right? So at 8 minutes, yeah.
I understand why we can't do that, but I can sometimes use placebos like broken bones. That should
Yeah.
is that okay? And
I will argue that I don't know if that's true.
but like the idea is.
But the point is to kind of provide, you can't prove that, but you can provide evidence that
Yeah.
it's unlikely,
Okay.
which is two different things.
Yeah.
Yeah. No, I just wonder if that makes sense, or you still Oh, I see what you mean. Yeah. No, I agree. And that's fine. If one of them is something that more, one is that more. Yeah, but if you have, okay, so it's getting to your point. Like if that violates, we agree on that, then think the most All right, let's go. Let's start. All right, so now after we, guys, let's go back. So now that we established that, where the literature is, guys, if you can just be a bit quiet. All right, thank you. So now that we established that, where the literature is, or was at least, and what are the issues and some of the methods that we might want to use in order to solve that, we're going to go through a few papers and see how these methods can actually help us to really understand better this kind of relationship between air pollution and variety of different outcomes that we're interested in. The first paper is a paper by Reed Walker and Wolfram Schlenker, published in the Review of Economic Studies in 2016. All the papers are outstanding here. This is why I select them. I think the first time I came across this paper was, I think it was 2012. I was at the NBR Summer Institute and I met Reed Walker. He was on the job market back then and he was telling me about this paper and I was like, no way, this is an awesome paper. So let me kind of walk you through what they did here. So the paper aimed to estimate the effect of contemporaneous air pollution exposure on observable health outcomes, specifically visits to A&E or emergency room in the United States. What's the identification issues? This is kind of what they write in the paper. Essentially, they're concerned about omitted verbal bias. So this is some of the things that they are talking about. Pollution is rarely randomly assigned across individuals, right? So it's not that, individual living area with high pollution are the same as, necessarily the same as in terms of characteristics and specifically health compared to people that live in less polluted areas. Also, preferences for clean air may be correlated with unobservable determinants of health, for example, exercise or diet as well, which again can lead to issue around omitted verbal bias, and also heterogeneity across individual in their preferences for or health response to ambient air pollution imply that individual may self-select into location on the basis of basically all the points that they're making in the paper is around, I think, OBB. Pretty much. All right, so this is kind of the issue. What did they do? They thought we need an instrument, all right? And this is what they had in mind. They use variation in local air pollution driven by airport runway congestion. Okay, this is a picture, I think, of JFK. Basically, airport runway congestion is measured by the total time spent taxiing between the gate and the runway. So taxiing is not taking a taxi, it's basically the time that the aircraft is leaving the gate and is about to take off, right? This is basically when the aircraft, the engine's on, and it's extremely polluting. Okay? Not great. And they thought, look, if we can have that, right, and there is some variation there, maybe we can use that as an instrument. For example, let's say, forget about the FK, we have data on health in around Los Angeles, right? We can have some data on taxi time, variation in taxi time in LAX, which is the airport in LA. Can we use that as an instrument for local air pollution? What do you think? You think that's a good idea? Yes or no? Yeah. For example, you can do that, yeah. You can be not just really around, but you can be, we talked about the decay function before, so it will travel a bit with space. But you can just look at people that live, it's contemporaneous, right? So kind of people that live in the same area, but sometimes they're exposed on kind of daily variation in pollution that is driven by the taxing time in LA. Say again? It probably will go a certain distance. Oh, you're talking about, okay, gotcha. You're talking, okay, I understand. Whether you can generalize from the results of this study, kind of the external validity, that's what you're talking about, right? Which is a fair question. But what I'm talking about first, which is a very good point, is about the internal validity. So I'm thinking about whether using taxi time in the way that I described it So using variation in taxiing time in LAX as an instrument for pollution in LA area, areas that will be affected by that, to maybe different degrees, and whether that's going to be a good instrument in terms of the internal validity. Yes.
One potential issue I think of is that it's not really random when taxing time increases.
Okay.
You have holidays like Christmas, Thanksgiving in the US, and maybe that correlates with other health outcomes.
Okay, no, that's a good point. So can I just basically omit these days? So the holiday days when there is, can I do that? That's going to be sufficient for you? What do you think? So like no, nothing around Christmas, Thanksgiving, around school holidays, nothing around that. Okay, yeah.
Even though, like, when does taxi time also increase when you have certain weather events? Therefore, then they, like, there's a storm coming, then they have to taxi for longer, and therefore also.
Yeah, yeah, yes.
How close is the airport from the city? Because if it's
I mean, it's in LA.
oh, it's middle of the city.
It's part of LA.
Is it like
I mean, it depends on how you define LA. I mean, it depends on exactly, but it is in kind of like, I would say, been there quite a lot of time last year. It's kind of more central South LA.
in that case? There's also the other issue of like people who live near the airport tend to be poorer, and that has other health.
Okay, you put fixed effect on where people, on the hospital, right? So
Yeah.
people are kind of near the hospital. So if you have the hospital admission, you can do that. The fixed effect you're going to deal only again with time invariant factors, right? Potentially an issue for what you were mentioning and some of the things that you mentioned. Yes.
Yes, so I think it should be, so it depends on the outcome we're looking at, right? And I think,
Hospital visits.
okay, so then it's going to be looking on, so it should be exogenous to that.
I'm asking that's my question.
No, exactly. So, I can't say that it's related, but I think the type of pollution that we're looking at is going to be pollution that's got a short-term consequence. And as before, we're looking at the difference of life expectancy, for example.
Oh, well, I mean, short term. Yeah, no, that's a good point. So, totally, no. So there are two things. Here we're talking about short-term exposure. By the way, short-term exposure can have long-term impact. But we're totally talking about short-term exposure rather than, or short-term exposure and how that affect hospital, not even admission, it's visits to A&E, ER. But yes, anyone else have another comment before I kind of wrap it up? So you made some good points. I'm just being a bit difficult. The point is that you're kind of right. It is good, but it's not just there because of some of the things that you mentioned. You were talking about holidays, you were talking about weather, you were talking about lots of different stuff, right? The thing is that there's many things that can change over time. And we can't control for every single one because some of them are observed, some of them are not. And they know it's an issue. For example, weather. You mentioned weather. We can control for some weather, but also if we control, by the way, if we control, do we control for that in the right way? That's another question, because if we don't, then it's not solved the whole issue as well, right? And what about all the interaction and some of the things that maybe there are something that we don't even know that we need to know. That's my point, all right? And Reed and Wolfram knows that as well. So they don't actually use the taxiing time. This is the beauty of this paper. They don't use taxi time in LAX. They're actually going to use taxi time in other major hubs, major airports in the United States that are connected to LAX, places on the East Coast. So LA is on the West Coast, right? Places on the East Coast that basically, if they have some problem there, let's say there is a weather event, which is not unheard of on the East Coast, right? For those of you that know, and you can, basically there is travel chaos, right? That might affect traffic in LAX. Even though what happened is completely on the other side of the United States. And the United States is a massive country, right? So there is an event going on in New York or in the Midwest in Chicago or something like that. That has an impact through this kind of network, right, of planes, and that affects taxi time in LAX because now there is issue and lots of cancellation or something else going on because of, flights coming from New York, Chicago, and all these kind of other major hubs. So they're going to use taxi time in Chicago, in Atlanta, and in JFK, major hubs on the other side of the country, as an instrument of what happened in LAX, okay? To pollution, actually, in the LA area. And then, we were talking about, you remember this guy, second thing that we need for an instrument. This guy here. Look, the first stage, I'm going to show you the table. Easy. When Reed told me about this paper, I was like, no way you have a first stage. And he was like, oh, I mean, you can look at a table, right? Yeah, fair enough. Then the second thing is about that, right? Is that exogenous, right? Is that the only channel, the exclusion restriction, that can make sense here? And I think it's fair to say that it's probably the case, right? Because basically what I'm saying is that something happened in New York. Other than that, how is that going to affect pollution concentration in LA? Right? So this is what they do. And this is why I think it's genius. This is why it was published so well as well, right? All right, so let me kind of walk you through more of what they did here. So since local runway congestion may be correlated with other determinants of pollution, such as weather, as you said, they exploit the fact that California airport congestion is driven by network delays that began in large airports outside of California. The analysis hence links health outcomes of residents living near California airports to changes in air pollution driven by runway congestion on the other side of the United States. Okay? So the identification variation in pollution is caused by events several thousand miles away. For example, weather in Atlanta, weather in Chicago, weather in New York, not weather in LA, which is, I think, and they think, unlikely to be correlated with unobserved determinants of health in California. Okay, so again, something that miles and miles away happened through this network of planes affect LA pollution, LAX pollution, and therefore this is what we get. So let's kind of look at some of the, basically this is the map, right? So this is kind of the different airports in California, right? And what they're going to use, three major airports on the other side of the country, so Chicago, Atlanta, and New York, JFK in New York. These are all giant airports, okay? So you can imagine that if something goes wrong there, it's going to have impact on the entire network, okay? It's totally believable for anyone that lives in the United States, I think. So what you see here, this is kind of first stage, I guess, regression in a way. This is taxi time at California airport on East Coast taxi time. So this is basically the correlation between the taxi time in Atlanta, Orlando, and JFK, and different airports in California. The first one is with LAX, okay? And what you see that basically they are very highly correlated. Taxi time in Atlanta, Orlando, and JFK. And Chicago and JFK. Okay? Interestingly, for example, in some point, you see that there is a negative correlation and not positive. Anyone can think why you're going to see a negative correlation, actually? Yeah. Exactly. So if there is like chaos with flights, so think about, for example, flight between LAX and Santa Barbara is a smaller, it's a tiny airport. It's a beautiful tiny airport. It's so beautiful. You can come to the airport literally 20 minutes before your flight depart because there is never a queue, and once you cross security, which is like basically like two guys, you are at the gate. Like literally, that's where the security is. I'm at the gate, right? So, and the reason is that I think there are 12 flights a day, okay, going to LAX, San Francisco, I think Atlanta, Denver. But anyway, the point is that it's not a massive airport. And what happened, the first kind of cancellation will be the flights that going from Santa Barbara to LAX because you can just drive. Okay, if there is no traffic, it's around an hour and a half. If there is traffic, good luck. But this is some of the things. So this is why you get the opposite direction because you're actually going to get cancellation, as you said. All right. this is pollution regress on the instrumented taxi time that I said. So you see this is kind of the taxi time, and this is kind of different type of pollutant. So we're going to focus more on CO and NO2 because O3 is basically ozone. It's a secondary pollutant, so it's a bit more complicated because other things affect ozone. It's also weather stuff as well. So it's always a bit more tricky to deal with that. But basically what you see that taxi time, instrumented taxi time, so again, taxi time that's instrumented on, not in LAX, it's instrumented with taxi time on the other side of the United States, have an impact on CO pollution and NO2 pollution. Okay, so this kind of, we have this effect. So we have this finding. This is not actually what we're really interested in, right? Because this is just taxi time on pollution. I got carried away about how amazing the identification strategy, but what we're actually trying to study here is health, right? So this is the effect on health, right? So again, this is kind of instrumented taxi time on different health outcomes. So this is on things like asthma, acute respiratory, all respiratory and all heart. And you can see that basically with this instrument, you see an increase in visits to A&E. This is not admission. The difference is that admission is that you're going to spend overnight. This is not necessarily spending overnight. You basically just arrive to A&E, okay? And this is what you have for all ages. Then, according to the literature, you expect that there are some sensitive groups. Sensitive groups is normally kids and elderly. It's really below 1, but also below 5 are more affected. It's just because their systems are not fully grown. They are just more sensitive to pollution, specifically below 1. But overall, think about below 5 and above 65. They're just more vulnerable to pollution. So you would expect that pollution is going to have more impact, specifically going back to your point, contemporaneous effects. They're going to be more severe. And this is kind of what we see here as well, right? We see the point estimates are larger for these groups, okay, compared to other groups, to the all ages, okay? So people kind of our ages tend to be less, again, everything else being equal, are less sensitive to pollution variation in the short run, okay? Again, if you have some medical condition, for example, asthma or some other stuff, yeah, you might be more sensitive, of course, right? So that's what's going on here. Another really cool stuff is kind of trying to convince the reader, yourself, that what they got here is correct, is they thought, look, this is all the stuff, like, asthma-related issue or heart-related issue. This is all the stuff that we expect pollution to cause. But let's regress it also on things that we think are completely unrelated to pollution. For example, bone fractures, right? They didn't think that bone fracture might be correlated with pollution. So why, when we have higher pollution, we're going to have higher bone fracture, right? So they basically run this kind of placebo test, right? So they regress that with the instrument on things that they think that are correlated and hope and confirm that should not have any impact. And this is exactly what they found on appendicitis, bone fracture, and stroke. Things that should not be directly related to air pollution. Lutz Sager, I mentioned him before, actually has a paper on air pollution and accidents. So I would argue that might not be a good placebo. Actually, I have an ongoing work now. We have a paper, it's not out there yet, about work accidents and pollution. We find evidence across the United States, and we found strong evidence for that. So I would say that column 4 not necessarily going to work as a placebo, but it's new evidence, right? So it's not something that we knew in 2016. I mean, to be honest, they had a full version of this paper in 2012, okay? But just kind of highlighting that. But I think it's kind of a nice thing to do these placebo exercises, all right? And again, when we say we're doing this placebo exercise, where is it coming from? It's coming from the same setting that we are trying to mimic, from this RCT, right? Because in medical experiment, what they do, right? They do this kind of randomized control trial. They give, the treatment group the real drug, and what do they give to the control group? A placebo drug, something that looks exactly the same, but it's not. So this is where the language is coming from. Again, everything that we try to do here is to mimic this gold standard, okay, of experiment. It's not perfect. Nothing going to be perfect here. We're trying to do as much as we can to reduce, uneasiness around that. Yeah, what's the difference between this and this? I don't remember. But anyway, this is kind of the main results of the paper, different models. Yeah, again, all significant, seems pretty strong also in terms of the magnitude of the results, et cetera, et cetera. So it's a great paper. Another paper, another great paper, yes.
If I remember correctly, the link that they were establishing on why the traffic congestion in other airports might affect the health outcomes in LA was because then these planes, because of the delays, these planes will stay more time like flying over because they couldn't land because of the.
No, it's actually about the taxiing time. It's basically how much congestion you will have. So the congestion that happened on the East Coast, it's basically all coming. It's not from flying above. It's actually spending more time. This is basically going. It's basically the point. It's this point here.
Yeah, but what explains then? What will be the causal explanation for the increase of pollution in LA? Because the taxi time there is not polluting, so there should be.
No, but it affects landing and it affects traffic in LAX because you need to wait until you get a slot and the engines are running and you're just waiting until you get that.
While you're flying over.
No, but also before departure.
But then before departure, the pollution is in other.
No, but that's the point. If you have anything that happened on one side, it can also have an impact on another side through even on the ground in terms of how they're taxing. So, for example, if you want to travel from Heathrow, all right, just give you a different example. Well, it's related. And there is some issues with air traffic control in Europe. Your airliner probably want to put you on a plane and try to get you a better slot as quickly as they can to make you, so once they have it, you can fly as quickly as possible to kind of, reduce the time that their airplane is essentially not in the air. So they're going to put you on the plane, and they're going to take you away from the gate because they need the gate for other as well. And you're going to go, and you probably, for those of you that flying a lot, you've been to this situation, you can be like potentially an hour waiting for your slots, waiting for your departures because there is chaos around. Rather than just like, we know you're going to take off in 10 minutes, you basically leave the gate, go to the runway and fly. This is kind of how it works, if it makes sense.
But then is my time in that airport affecting?
But what led to that, so with my regression, I'm going to basically use the taxi time on the other side. And the point is that what happened on the other side affect also the taxi time, as I'm showing you here, in LAX. But it's not driven by things like, it's basically what this is what is so genius, this instrument. Because it's take the bit that is uncoded with all the things that we were worried about, the holiday, the weather, all this stuff. Because it's being driven by what happened on the east side. Okay? All right. Not my paper. If you don't like it, speak to Reed and Wolfram. Okay. Another paper. Here, that's my paper. So that's actually 2 chapters of my PhD are here. Let me tell you how we thought about it. This is going back to 2010 or 2011, when we started, I think 2010. So it takes a lot of time to publish in economics, I can tell you that. And this is with Avi Ebenstein from the Hebrew University. You probably read one of his papers in 426, 428, sorry. It's about the UI River policy in China and kind of the discontinuity. Maybe you haven't done it yet. You might want to do that around discontinuity around the river there and how that affects life expectancy. Great paper that published in PNAS a few years ago. And Victor Lavi, which is a professor at Warwick, and he was my PhD supervisor. And basically what we were thinking, look, there is all these health outcomes that people show that air pollution has an impact on, right? But most of them, at least back then, were like on big stuff, like heart attacks, mortality, all these kind of big things. But we were like, look, as I showed you in, if I'm gonna go lots of slides ago, where is it? This stuff here, right? Irritation of the eyes, nose and throat, headache, dizziness, all these kind of different things might affect your cognitive performance. And it might also, something like PM 2.5 might also have an impact on your cognitive performance or even your cognition, which are two different, related but different things, through what I said in the beginning, that PM 2.5 can actually enter your bloodstream, and there is some kind of literature that suggested back then that, again, unconfirmed, but that it might also have affect your brain directly. So we were like, let's test that. Let's check whether people that are exposed to higher level of pollution have worse cognitive performance, okay? Now, the problem that we had here is that, now it's kind of obvious, but I think it's one of the reasons because we wrote this paper, is that how are we going to measure cognitive performance? It's not that easy. So what we came up with is like, let's look at test scores. Let's look at how people perform in their tests. Okay? So we got this amazing, this kind of basically what I said. We got this amazing data on basically everyone that took exam, high school exit exam in Israel, the entire population that took their exams at the end of high school. And each person there takes around, it depends a bit, but around 5 to 6 exams. Okay. And these exams are quite important because they are, crucial for your higher education. Okay? So we managed to get the data, it's crazy. We managed to get this data from the Ministry of Education. Okay? For everyone that took the test. Between 2000 and 2002, we also knew exactly where they live. This is data from the government, right? We knew everything about them and about the parents. We know where the parents were born, how educated they were. You name it, we knew it. Fantastic, right? This is why Scandinavia and Israel produce like really nice empirical papers, because we have this data. And everything can be linked because everyone that's born in Israel have a unique identification number. So we can link it with lots of different data sets, and they can link it as well. And we got a file that connect all of it together. Remember that I tell you that each student take around 5 or 6 exams, right? And these exams are, the date of these exams are determined well in advance. So, for example, your whatever test that you need to take in June, the exact date of that will be determined probably around January. Okay? And we know exactly where you took the exam and when. And there is a good network of monitoring stations for air pollution. We managed to link that together. So we have data on air pollution. We have data on students' exams. Okay? And what we can do together now is to use a fixed effect model to estimate within student variation, right? So now I'm not going to compare you and you that live in two different areas, which expose to different level of pollution, because this is not comparing apples with apples. Okay? I'm going to compare you with yourself, sitting in an exam, right, with different environmental conditions. And because the exams are determined well in advance, I think that the level of pollution on the day is completely orthogonal to the exam that you actually take. And that's the identification assumption. So it's this combination of these two things. The other thing that you might worry about is about marking, right? Is it about the exam taking place, or is it about the supply side, the teacher side? But in this case, in here, marking is not on the same day, after that, so you shouldn't worry about that, right? So this is what we had in mind. Is that perfect? No. But, it's kind of towards, something reasonable, yes.
But isn't it still the subject that the people doing the exam different?
Totally. So yes, but this is the point that I'm making, right? Because the date of the exam were predetermined well in advance. So whether you take a math or an English or whatever test that you take, right, it's predetermined and just that's completely unrelated to pollution on the day.
Yep.
So it is as good as random. We also have in the paper, or I don't know if it's made the final paper or it's in the NDR version, when we basically look at within subject, or we group it together, STEM versus no STEM, the results are the same. Because it's coming from the same point that I'm making before. It's this combination of two things. The variation within student and the setting that we had that is predetermined. So it's important to have both of these things together. Again, it's not perfect, I agree. You can worry about some other stuff, for example, in reverse causality, and I can talk about it later. But that's what we had in mind, yes. Oh, we did. Yeah. Sorry, we have time. We have day of the week, and we have all of this stuff as well. Month and blah blah blah. Yeah. I didn't show you the regression. Yeah, we have. Yeah, it was published in a pretty good journal. They asked us to do lots of different stuff. But yeah. And what we found that there is an effect. Now it's kind of there are no stars here because my supervisor hated stars in like for significance. He like takes all the stars away. All right, fine. He's a kind of old school, graduated from PhD in Chicago in like 1978. It was like determined like, oh, you got something wrong. Because how do you know? You take pen and paper and derive some of the stuff by itself. I was like, wow, okay, old school. Anyway, what we have here, this is with a student fixed effect. You find a kind of significant impact on student test score, right? So it's basically this guy divided by here. Obviously, you consider this is the t-stat. That's kind of significant. Here, we're talking about relatively large sample size. In terms of the effect, I mean, it depends on how you kind of interpret the effect. But if you think about like a polluted days, like really, comparing polluted days to non-polluted days, the effect is massive. So another paper that Victor Lavie has, it's a famous paper about discontinuity design. It's about class size. It's with Josh Angris. I don't know if you read his paper about the class size. If you're above or below 40, this is the paper together in the QJE. So their paper is kind of similar to, in terms of our effect, if you would cut, if I remember correctly, move, gosh, it's been a long time since I wrote the paper. If you move class size from, what was that, 35 to 25? I don't remember the exact time, but it's a significant reduction in test scores, right? So this is what we found. The story here, actually, I'll give you some inside gossip, is that actually we had two different papers. If you go to the NPR Walking Paper Series, you will find that we have two papers. And then the editor of, actually both of them were revised and resubmitted in two different journals, and then the editor of the AHA suggested, oh, why don't you kind of put them together, and that's going to be a really cool paper. And let me tell you what we did in the other paper that at the end, we ended up putting it all together, and I'm glad that we did that. We actually had a meeting here at LSE. I remember that we were like thinking, should we do two papers or one paper? We decided to go with one. But that's going back to your point, actually. So we were thinking, okay, this is really cool, but this is what happened on the day. What's the impact on the test score right now? Well, I told you that these kind of tests are high stakes. They are important because these tests will impact your higher education and therefore might also have an impact on your earning later in life. So going back to your point, we're talking about a short-term exposure which might have long-term impact. Because think about the following story, right? You go to a high-stake exam, all right? And you don't do that well. Instead of coming to LSE, you go to another university, which I'm not going to tell you which one I have in mind. It's nearby. Therefore, your earning potential might be affected by that. No, I mean, I'm being serious, right? Because that has an impact. Now, that has a serious impact, not just on you as an individual, right? That actually has an impact on the labor market as a whole, because you guys can be both as talented as you are. Let's say that you're equally talented. So I keep picking on you. Let's move to these guys. You both are equally talented. You just had a bad day in the exam, and therefore, you're going to LSE, you're going somewhere, you said that. I have something else, somewhere else in mind, but never mind. Right? So you are more likely to earn a higher wage. Okay? And this is just because he had bad day in the exam. So what we try to do here is to go back to the government, ask them for more data, which we did, and ask for the same cohort that we have, whether we can look at their earnings 10 years after that. And also whether we can get information about their higher education. All right? Actually, I'm part of the sample, by the way. I actually found myself in the data. I just want to verify that it's inside. How do they have all this information about me and my girl? Scary, but super helpful for research, right? So we did, hold on for 1 second. So we did that. And then basically what we did, we look at like, okay, what happened to your completed years of post-secondary education, whether you even went to post-secondary education. In the paper, we have more, which post-secondary education did you go to, the Hebrew U, which is a really good university, or other places, this kind of stuff, okay? And also, what was your average monthly earning 10 years afterwards? So this is just in shekels, it's like all time, so I'm just gonna tell you, this is around, the effect of lifetime earning is around 2%. 2.1%. That's a massive one. Basically, we showed the whole churn of events. You had a bad day on the exam, didn't come to LSE, you went somewhere else, you're earning 2% less. Now, this is also, as I said before, this has an effect on allocation of talent across professions in general. This is kind of a point that actually Michael Greenstone made to us when we presented this paper at the MBR Summer Institute. And I think it's a great point. Because basically we have this kind of relatively noisy measure, right, that we use in order to allocate, right, workers to professions. And that kind of disturbed this thing. By the way that we sold this paper at the end is that we said, well, it's not about pollution, it's about having a bad day on an exam, and why high-stake exams are not necessarily a good thing. And we basically, I was in the job market for this, so it depends on where I presented my paper, if it's more education kind of position or more environmental position. But you can tell these stories like, look, you care about pollution, super important. If you don't care about pollution, don't worry about pollution. You had a bad day, I'm not going to look at you. You had a bad day on an exam. It could be that you had a high pollution day. It could be that your partner broke up with you. It could be that you had a noisy neighbor. Whatever happened. These are the consequences. So why high-stakes exams are not necessarily bad? Not necessarily great, okay? This is what we had here. Gosh, I need to move on. You had a question?
No, you understood that.
Okay, even better. All right, so this is what we did here. We don't necessarily need to just use fixed effect or IV. We can use both of them together. So this is another paper with Malvina Bondi, a former ECC student, actually, which actually I just saw her the other day on the street. She lived not far from me. And that was part of her dissertation. So we had this idea, and I was like, Malvina, why don't you work on that? Let's see what you get. And she got some interesting results. By the way, this is not the final version, what you read in the paper. This is not the final version of dissertation. She just had fixed effect there and doesn't look like that. So we are not expecting you to have this level of dissertation, but it started as a dissertation, okay? And Lutz was around as a PhD student, and I told you about Lutz before. He's a great researcher, and we have a few papers together. And we were like, okay, so, we know that air pollution affects a variety of different things. Let's see if it also affects crime. We had some cool data on crime as well, so we're like, okay, we can do that. I was thinking about crime since 2011, I think. But I said, like, I don't know how I can deal with that, with the issue. But it's kind of, we had an opportunity to I think, to deal with many of the stuff here, so that's what we did. All right, so what did we do here? Unique, everything is unique. We had a data set, it's not that unique. We had a data set which combined reading of daily ambient air pollution concentration from London with rich admin record on over 1.8 million criminal offenses essentially from the Met Office, from the Metropolitan Police between 2004 and 2005. So we got daily data on all the crimes. We know the type of crime, we know everything. Okay, so around 1.8 million criminal offenses over this period. To deal with econometrics issue, we do two things. We do fixed effect models and IV. And here we provide one of the first evidence that there is a link between air pollution and criminal activity. This is kind of what we use. So this is a map of London. Each one of those regions here is what we call wards, right? So we have lots of wards in London. We have also, boroughs, whatever, but we use wards. All the red dots here are basically the the pollution and weather station that we use for our study. So relatively good network that we had. Back then, we have even better one. This is just kind of how the data for pollution, for example, look like. We use AQI, which is Air Quality Index, which incorporates all the different pollution because we were worried about exclusion restriction and things like that. I'm happy to talk to you more about it if you're going to work on air pollution. And then what we basically, before I kind of show you the results, basically what we did here is that two things. One, we didn't want to compare, for example, Kensington, which is a very affluent area of London, to less affluent area of London, because we, as I mentioned before, it might be that these places are very, very different on a variety of different outcomes, and that's not going to be like we like. So what we can use, we use the panel structure of the data because we have the same location over time, and we can do a fixed effect. Okay, so we compare, for example, Kensington with itself over time, see how variation in air pollution might affect. So this is one strategy. But you can tell me, hold on, Sefi, that's a bit of an issue. That's what you're going to tell me? It's problematic?
No, I was thinking about temperature because it's also crime is also very temperature.
Totally, and we control for temperature, you're absolutely right. But the question is whether we control for that sufficiently. But that's a good point, we control for that. But it could be that, yes, so it might be that that's going to deal with time invariant kind of confounding factors. But what about things like reverse causality? Remember that I mentioned that before? So reverse causality, what do I have in mind here? Well, if there is crime, let's say, now there is more police coming to the area, potentially traffic congestion, and then we see more pollution. So is it the pollution that drives crime, or is that crime that drives pollution? It's kind of the chicken and the egg, right? So with reverse causality, fixed effect not gonna able to help us, right? So the second kind of strategy that we had in mind here is that we're going to use the wind as an instrument. Okay? So what did we have in mind here? Sometimes the wind is blowing from west to east, sometimes from east to west. Take pollution at almost random from one part of the city to the other one. On a daily basis, I think this is a good instrument because it, on average, long term, maybe people saw it, depends on wind, so that's a bit of a problem. But on a daily basis, I think that the wind direction is as good as random. So we're gonna, essentially what we're gonna do, hold on, we're gonna follow the wind, that's gonna be the first stage, see the wind direction and see whether pollution is going towards where we think it should go. And then we're gonna use this wind direction as an instrument for pollution. This is kind of really high level, there is more discussion in the paper around that here. But that's the point, it's prevailing wind direction.
But doesn't that mean that on average on each day the probability of it?
Yeah, but if you for example, you put something, I agree with you. This is why you don't want to do it, for example, at the unit level. But let's say that I'm incorporating that with fixed effect of location, or a slightly greater location. Or I control for it also depends on the time of the year, right? So I control for some time fixed effect, someone mentioned before. With this kind of stuff, again, nothing is bulletproof, but it gives you some evidence. So I think that on a daily level, that's a pretty good instrument. The other thing that I want to say, like, look, if nothing is perfect, but you put lots of different stuff and it all kind of point to the same direction, I think that's reassuring, right? Anyway, I'm not going to, anyone else? All right, so this is kind of preview of the results. You see the kind of strong correlation. This is basically, I just kind of show the residual AQI and the residual log of crime. So this is kind of where I basically use the fixed effect on both of these outcomes and kind of plot them together. I use lowest here just to kind of make it to force, not to force shape on the functional form. But this is kind of the results. This is the results in terms of the fixed effect, PPML. It's also a count variable, that crime, right? So it's number of crimes, so you need to think about that. So you want to use something like Poisson, right? something like that to count for the nature of the study. This is what we did here. And this is when we have non-linear effects, so it might be that we worry that the effect is non-linear, so it's not that every additional unit of PM has the same impact, so we kind of use different beams, so to speak, of pollution level. And this is with the IV. The point is that whatever you do, the effects are positive and strong and not that different from each other. We also look at the type of crime, which crime is affected, and we have the whole discussion in the paper why we think certain crimes are affected and some certain crimes are not, mainly whether they are kind of more spontaneous or less spontaneous. And this kind of also point to your prevailing wind story, I guess. Right, so we saw that air pollution is linked with morbidity and other well-being outcomes. How is that related to economics? So first of all, I kind of show you the effect on earnings and things like that. It's obviously linked. Think about health that come with massive costs to the NHS and also to individuals. But also, all of this is related to what we did before, right? The marginal damage. This is basically one way that we can think about the marginal damage. The functional forms that I mentioned, does the marginal damage look like that? Does it look like that? Or does it look like that? That depends on what you actually find in the study. And this is what we're spending a lot of time thinking about. Also, what I want to mention here is that, look, what we have here is a dollar sign. Everything that we had before, it's not really dollar sign. It's about crime. It's about education. Most of the stuff is about education. Here we actually have something on monetary terms. But a lot of the stuff here was nothing to do with money, right? So we kind of have to do some more stuff about thinking how we convert these estimates to basically to monetize it, all right? So if we have, for example, we're thinking about the paper by Reed Walker and Wolfram Schlenker, we can use something like the cost of illness method. So the total cost defined as the sum of direct and indirect costs, right? So the direct costs include hospital care, home health care, services of physician, and drugs. So we can think about all the costs that are associated with visits to an A&E. And also the indirect costs measure the value of loss in productivity to the illness. For example, you lose some time because you're not at work, and we can combine all of these costs together. It's a bit of the back of the envelope calculation, but we can use that in order to get some kind of guesstimate around the cost. Not perfect, but we can use that. So two-step procedure, essentially you're going to get a dose response function. This is what I showed you before, right? The pollution effect on hospital visit, for example, and then estimate the total direct and indirect costs attributed to pollution by applying the cost of illness method to the dose response function that we had before. It's not perfect, lots of criticism around that, but this is kind of in reality, and we should definitely do more on that. Most of this kind of cost estimated, it's kind of in appendix A17 of the paper, and it's somehow also making it into the abstract. But a lot of it is really back of the envelope calculation. We should definitely do more on that. The problem becomes more severe when we think about how do we value mortality? I'm not going to pick on you again. What's the value of your life? Oh, wow. Okay. You should upgrade your estimate. But this is something that is very, very hard, and I don't have time, and it doesn't really work here, unfortunately, the video and the sound. But this is kind of a great link to the Jack Benny radio program. So if you have time at home, just watch that. It's like maybe 40 seconds. But the point is, if you ask someone, what's your life? I mean, was an outlier, I suggest. People say, like, look, or if it's real, you say, I'll give you everything I have, just I want to live, right? In most cases, you would expect that. In here, they obviously make a joke about that. But the point is that, we need to think about it from like a greater point. And one way to do that is to think about something called the value of statistical life, right? In short, what's the concept here? The concept here is that people make this trade-off between, for example, saving some time and increase the probability of dying. Sounds crazy, right? How many of you crossing red lights? There you go. You know that you increase, even by a tiny bit, the chance of you dying. But you still do that. Why do you do that? Because you want to save some time. How many of you or driving above the speed limit. You don't have to say that. I know it's recorded. Right? But again, you make a conscious decision or unconscious decision to speed up, increase the probability of dying because you want to save time. And if we have some information about these two elements here, we can back up. Nothing is perfect. I keep looking at you because you say, well, it's not great, but everything that we do here is not going to be perfect. It's not a criticism, it's a great point. But we think economists feel that this is the best we can do. By the way, in COVID years, that's something that was used quite a bit, or something like that. But this is what we call the value of statistical life, right? It's this kind of the ratio that I basically describe now. It doesn't have to be traffic related. It can be, for example, job, right? We're willing to take a job that is slightly riskier because we get some more money for that. Yes.
I was just going to ask about that.
Totally. Absolutely. Absolutely. So this is kind of where it's coming from. The V star here is the kind of the change in W, the wealth, over the change in P, which is basically the chance of, of fatality, right? And you can measure that in different ways. One, you can use stated preference. Ask, people. Not a big fan of that. You might have figured that. But then you can do review preference method, right? And using a Donick price method or whatever. And there is a great paper by Oli Aschenfelder and Michael Greens about speed limits in the United States. This is a JPE paper from 2004. Again, using this kind of variation in state speed limit to get something around that. If you know something about people's wealth or income, something about this stuff, you can back it up. Not perfect, but something to work with. Because at the end of the day, this is necessary for making some decision on policy. In the last 3 or 4 minutes that I have, I just want to mention a few things that kind of to be more optimistic. Because actually in many places, in some places in the world, we see really kind of sharp increase in pollution concentration. In some places, we see a significant reduction. If you look at the United States, if you look at London, forget about the United States. I talk too much about the United States. Overrated. They not. I like that, but we are in London right now. When I started teaching GY426 in 2016, I always had a slide of like how long it took London to reach the annual, level of pollution that we had. First year, I think it was 24 hours. Second year, 2017, again, I don't remember exactly, but it's something like that. Second year, I think it was 48 hours. 2018, maybe 2 months. And now, we're pretty much good. All of that comes through policy. Okay? So when we want to do something, we can do something about that. Okay? Also, we don't have the London Great Smogs anymore. Why is that? We still have these inversions, I can tell you. I have a whole paper on that. Actually, in the crime paper, we also use inversion as an instrument. I remember now. I forgot about that. We have 2 instruments there. Forgot. But we also have another paper that we kind of document all these things about inversion. If you're interested in that, this paper that was published, I think, 2 years ago. It's still happening, but we just changed policy. We reduced the emission in London. All right? So there's lots of things that we can do about air pollution. One is to reduce by policy or things like that. We can also try to avoid, because I told you what matters here is not necessarily concentration, is exposure. And we can avoid. We can talk more about it on Wednesday. And you can use some defensive investment. You can buy air purifiers. You can do some other things. Okay? Which is kind of related to avoidance as well, to some degree, I suspect. All of these have costs and benefit. And in different situations, you might want to use something else. In a recent working paper, it's not a paper that was published, with Brian Shield, which was also an ACC student, actually, that was part of a dissertation. I'm going to work on that with Antonio, which was a PhD student in urban economics here at LSE. We were thinking about, let's look at the London LEZ and see how that kind of relate to, the test score paper that I mentioned before, but kind of longer term, whether we see an improvement in test scores following this LEZ policy, the low emission zone policy in London. We already had information that it reduced pollution. In fact, one of my colleagues here, Henrik Wolf, which is an expert in transportation, economist, he kind of showed a paper on that. There are tons of paper on health. They were like, no one did this education. I have this paper on education. Let's kind of link it all together to see whether we see the full change. changing policy, reduce pollution, improvement in test scores. So not just one or two kind of bits, the whole chain. And that's exactly what we did. And we got some cool data about key stage 2 results, which is the results, tests that students here take around age 11. We had data on whether you are in the low emission zone or not. We had lots of information that we need. And the way that we did that, we used basically diffs and diffs and matching together, comparing places that were subject to the low emission zone before and after the policy change to those that are far enough away. So this is the map. So this is London. This is where it was, the policy was affected. This is actually really important and nice way to think about it. I know that I'm maybe like 1 minute after time. So this is kind of the treatment group. And then we use other urban schools which are sufficiently far from London. And the reason why we didn't use these guys here, which is just around London within the dash line, is because it's kind of nicely linked to the lecture next week, because we know that pollution travels in space. So we don't know if that's a clean control group, because they might also be affected through pollution directly. And also, look, if I decide that low emission zone is here, that might also have an impact actually on traffic here, because people don't want to go into the low emission zone, so they're just going to go around. So that might actually increase. So in all of this point that I'm trying to make, we thought about that as another treatment group rather than a control group. So we have this treatment group directly treated, this treatment group that are not directly treated but potentially treated, and the control group is here. We do lots of different stuff there. Okay, you can read the paper if you want. Point is, we found significant improvement overall, and they are really significant. And this is not just on the day. This is we're talking about, long-term exposure. In fact, the longer the policy is in place, the higher the impact on KS2 results. All right? And this is kind of, we look at heterogeneity, who is affected, kind of low income, high income, all these kind of different things. The results is exactly what you expect. Concluding thought, air pollution is bad. And what you would need to read for the Wednesday seminar is the following paper. I'll see you on Wednesday. Thank you very much. Hey, how are you? Yeah.
Great.
We're going to talk about it on Wednesday.
So I have a feeling it might just be those people like, the clown never have how you actually do
It's been always like that, no? I feel like
one on Thursday that was actually here.
you guys always say that this comes
No. I think that that's a great idea. It can be like a nice experiment, although